So in our previous class, we were doing the weak acid. So in weak acid, we said that acids that are only partially or incomplete dissociated in the solution are called a weak acid. So this is basically the definition to express how the weak acids work, or in other words, how their properties are shown. Weak acids include most organic acids, hydrocyanic acid, hydrogen sulfide, and carbonic acids. So these are some of the properties which are shown by the weak acids, or in other words, we can say that these are the weak acids. Ethanoic acid is considered to be weak acid because equilibrium for the reaction lies far to the left. In other words, it tries to say that when we construct the equilibrium for the dissolution or dissolving of the ethanoic acid in the water, then it shows that the equilibrium is far to the left side, which means more amount of this reactant is being formed instead of the amount of the formation of the hydrogen ions, which again indicates that this is a weak acid. For the weak acid, there shall be more amount of the original acid instead of the amount of the ionic form of the acid. There are many more molecules of ethanoic acid than ethanoate ion and hydroxonium ion or the oxonium ion. Now, there is another example which says that sulfuric acid, represented by H2SO4, the sulfuric acid has two hydrogen ions that can ionize. The first hydrogen ion to ionize dissociates almost completely. So here in this example, we can see that sulfuric acid is being completely completely converted into the hydrogen ions and the hydrogen sulfide ions. Whereas the hydrogen sulfide, which is produced as a result of this reaction, has a weaker acidic properties as compared to the sulfuric acid. And how is it proven? How is it shown? It is shown in the form of this equilibrium reaction. We can see that in this equilibrium reaction, the hydrogen sulfide ion is basically converted into both hydrogen ions and sulfate ions, as well as the same ions are showing the reversible reaction to make the original hydrogen sulfide. So basically, in this case, we can say that the hydrogen sulfide ion is less acidic as compared to the sulfuric acid, which has the formula of H2SO4. So H2SO4 is more acidic. So although we know that that sulfuric acid contains two hydrogen atoms, but those two hydrogen atoms are basically dissociated into different steps. The first step, there is in the first step there is a loss of or dissociation of one hydrogen ion, and in the second step there is the ionization of the second hydrogen ion. But first is very fast, or it is very easily happening, whereas the second hydrogen ion is not completely hydrogen is not completely lost. It is not completely dissociated. Then we have the properties of the strong bases. Bases that associate almost completely in solution are called the strong bases. So just like strong acids, the property of the strong acid is in the similar way that those substances which are completely dissociated in water makes up the strong type of this substance. It can be acid or it can be a base. The group 1 metal hydroxides are considered in this category of the strong bases. And then about the weak bases which dissociate to only a small extent or incompletely in solution are called the weak bases. And the properties or examples included are ammonia, amines, and some hydroxides of the transition metals. So these are some of the examples. We have already seen that ammonia is one such type of the weak base which we already discussed or studied in the O levels or IGCSE. The amines is basically the functional group of the organic compounds, which we will discuss later on in the organic chemistry. And then at the end, we have the hydroxides for the transition elements. The transition elements can be copper, iron, zinc, etc. So the hydroxides of these elements indicate the weak bases. The next topic is about the pH scale. The pH scale can be used to identify whether a substance is a strong or a weak acid or a base. So basically, pH scale, which we studied in the O levels, indicated that this is the type of a measurement to indicate whether the solution is acidic or it is a basic. So we studied in the O levels that the range of the pH scale is from 0 to 14. This is the range of pH values from 0 to 14. And we also studied in the O levels that the value from 0 to less than 7 is a range of the acids, and the value from greater than 7 are up to 14 is the value of bases, whereas the value of 7 pH 7 is basically the neutral solution. So pH 7 indicates the neutral solutions. Then we have the acid solution have pH less than 7 and alkaline solution have pH greater than 7. Weak acid solutions have pH 4 to 6 and weak bases have pH 8 to 10. So when we can also tell from these pH values that there is some specific region for the weak acids and weak bases. For the weak acids, the range is from 4 to 6, which means the values less than 4 will indicate the strong acids, whereas the value greater than 10 will indicate the strong bases. So these are also some of the values to differentiate the strong acid from weak acid and strong base from the weak base. pH is related with the concentration of the hydrogen ions. Strong acids have higher hydrogen ion concentration and lower pH. So how do we categorize that any acid is a strong acid? We can we can regard this, or we can classify that in terms of the amount of the hydrogen ions present. If the hydrogen ions amount is greater, then it means that the acid is strong. Whereas if the hydrogen ion amount is less, it means it is a weak acid. So everything is about the acid. The acids are basically linked with the amount of the or the concentration of the hydrogen ions. Now we have to distinguish a weak acid from the strong acids. How can we distinguish them? We can distinguish them. Strong acid can be distinguished by their pH values, electrical conductivity, and reactivity. That's how we can differentiate the as strong acid and the weak acids from each other. First of all, we have the practical application of electrical conductivity. Basically, electrical conductivity means how good a solution can conduct the electricity through it, or uh, how better an electricity can pass through a solution. That's the practical use of this topic of electrical conductivity. We know that the dilute solution of the strong acids indicates that they are showing a good amount of the ions present in the solution. For example, if I have a strong acid HCl, then when it dissolves in the water H2O, it will be completely dissociated into its ion, which includes hydrogen ions plus the chloride ions. Now these ions indicate that there will be large amount of these oppositely charged ions present in the solution. When there's a good concentration of these ions present in the solution, then as a result, the electrical conductivity shown by the equipment, it is a kind of a small type of the device which has, let's suppose if I draw a rough diagram of this device, which is mentioned here as the electrical conductivity probe or electrode. It is kind of this size, this type, which has a pen shape at the one end. This pen shape is dipped in the solution of the of substance, whatever we have. So this device is connected with the measurement on which the electrical values or digital values of the electricity is shown in terms of the voltage or volts. Those voltage indicates that there is a there is some certain amount of the electricity which is passing through the solution. So if we have a strong acid, then it will form a good amount of the charges or the ions. These ions will help in the conductance of the electricity. So electricity will pass through such a solution in which the strong acid is present. So that's how we can indicate that a solution is of a strong acid. However, if the solution is made up of the weak acid, then the amount of the ions when that substance is dissolved in water will not the ions formed will not be of good concentration, and that's why the electrical conductivity will be less. In other words, we can say mathematically that uh, the strength of acid is directly proportional to the conductivity. If there is a good conductivity, then it means the acid is of strong type. The next is reaction with the reactive metals. So reactive metals are basically those metals which can easily react with the acids. And as we studied in the O levels, that the reaction between an acid plus metal of the reactive type, they can give two products. The first is the salt, and the other one is the formation of the gas, basically the hydrogen gas. So these two are the products of the reaction between an acid and a metal. Now, in these two products, the only observation which we can see in the solution is the formation of this gas, hydrogen gas, and we use the word fizz, bubbles, effervescence, like these words. These are used to indicate that a gas has been produced inside a solution. So if we have a reactive metal, then how can we tell the acid is of strong or weak type? It can be we can tell by the formation of the hydrogen gas. If there are so many bubbles of the hydrogen gas produced in the solution, then it means that the acid is of strong type, which means strong acid will give more fizzing. More fizzing is seen in a strong acid, but if the acid is a weak, then there will be less fizzing of the gases inside the solution. So that's how we can differentiate between a strong acid and a weak acid. The pH of the solution can also be measured using a probe connected to a pH meter. A probe connected to a pH meter or by adding an indicator. So these are the other ways to find the type of the acid. The pH meter or a probe is again the same thing, just like we said about the electrical conductivity probe. They are of the digital type of the devices, and we have a pen type shape or tube type shape connected to the device, which is dipped into the solution. If we have a solution of this type, and a pen will be and this solution contains the acid, then the pen type shape of the probe is basically dipped in that solution, and this indicates values on it. The values on this device of the digital type can be pH value, or it can be the voltage, which basically indicates the electrical conductivity. So if the pH value is shown on the device, it means we are basically measuring the pH of the solution. So again, we will recall the range of the pH values from 0 to 14, and we will say that the values are 0, 1, 2, pH value of 0, 1, 2, in that it means they are strong acids. But the value is above 3, for example, 4, 5, 6, 7, pH value of 4, 5, 6, not 7, but less than 7. These indicate the weak acid, less than 7. These belong to weak acid, but values from 0, 1, 2, 3, etc., these are the strong acids. Then we have the uh, indicators. The indicators are basically the compounds which change their color in the presence of the acids or the basic solution. And what do we do in case of the indicators? We check the endpoint of the indicator, because at endpoint the indicator changes their colors. Indicators have their distinct colors in the acidic and the basic media or solution. So by looking or by observing those color changes, we can tell that the solution is of the basic or the acidic type. Then we have the equivalence point for the neutralization reaction. The neutralization, as we know, is a reaction between the acid and the base. So equivalence point is also a term used in these reactions. Equivalence point is that point at which the hydrogen ions equals the amount of the hydroxide ions, or the moles of the hydrogen ions become equal to the moles of the hydrogen ions. Hydroxide ions and hydrogen ions are equal at that point. That point is called the equivalence point. We need to choose the right indicator to ensure the endpoint and the equivalence point are the same. So the choice of the indicator is based upon the equivalence point and the endpoint. The same type, this topic will be elaborated later on. We have to choose the right indicator for the pH range of the equivalence point as well as the pH range of the indicator. These two are basically merging in the same time, at the same time, at the same value. The indicator, as we studied in the O levels, is also the universal indicator. Universal indicator is not suitable to check uh, because the color ranges are basically continuous change in the color, just like a rainbow, in which the color range is from red, orange, yellow, green, blue, violet. So these color changes are in a continuous way, and a human observation varies from person to person. That's why a uh, different person will have a different approach to the value of the pH. That's why it is not suitable for the measurement of the strong and the weak acid or base. An acid-base indicator is a compound that has two different ranges of the colors depending on the pH of the solution in which it is placed. It changes color over a narrow range of the pH values. So what are these acid-base indicators? These are the compounds which are exhibiting different colors in the solutions. Now, this is a topic starting from where we have to discuss the titration curves, pH curves, and it should be kept in mind that this topic of pH titration curves is basically included in 2022 to 2024 syllabus, and the same syllabus is now almost 99.9% similar in 2025 up to 2027. This topic of titration curves and the relevant topics were included in 2022, and it was transferred or shifted from A2 to AS. This topic was transferred from A2 to AS, which means the questions of the AS type are limited. The questions are starting from 2022 onwards. So there will be less number of the questions both for the P1 and for the P2. But some questions of the P4 can be attempted in terms of AS or paper 2, but not all. Some questions of the P4 of these topic can be attempted. However, the MCQs type questions of this topic is very limited. Anyways, the topic is that when acid reacts with the alkali, a neutralization reaction occurs to produce salt and water. Acid-base titration can be used to determine how the pH changes occur when different combination of weak or strong acids react with a weak or strong bases. So basically, we do know that the neutralization is basically the reaction between an acid and a base. However, the combinations can be different. As we know that a strong acid can be strong and acid can be a weak, as well as a base can be strong and base can be a weak, which means we can have different combinations of the neutralization reactions. We can have the combination between strong acid with a strong base. We can have combination of the strong acid with a weak base. We can have weak acid with a strong base as well as weak acid with a weak base. So these are the four different types of the combinations on which we will discuss the type of the curves obtained as a result of the titration. So titration is basically the practical experiment which the students do in the laboratory. And we will then plot those pH values on the graph to check how the titration or the pH values is varying. Okay, here titration curve. When an acid is added to a base or a base is added to an acid, a titration curve is obtained which indicates the type of the acid and or base involved in the titration. It doesn't necessarily mean that the pH of solution is equal to 7 at the end point, because either the acid or the alkali or both may be strong or weak, so they are four possible combinations. So we will trace the pH values when the reaction of acid when there is a reaction of the acid with the base, and we will see how the pH is varying and how the equilibrium point or the end point is being shown in the graph. So let's start from here, the reaction of the strong acid with a strong base. All right, now we have the acid and we have a base. Basically, this reaction is being carried out the when there was initially the acid, there was only acid in the conical flask. We know the shape of the conical flask is like this. The conical flask contains only the base at this point. Sorry, it contains only the acid at this point, and then we use the burette to put the base into the flask. So a base is present in this burette. We start pouring down the base into the flask. So we will now trace how the pH values is varying as we do this reaction. At the start of the reaction, there is only the acid present in the flask, which I have mentioned here, the acid. Only acid will present in the flask, which means, and which type of the acid would it be? It was the strong type. Strong acid present in the flask, which means that if we start plotting the values of the pH change, then the start of the reaction will indicate that the pH value is at very low range. We know that strong acid can have pH from 0 up to 3 or less than 3. So you can see here that this graph is starting nearly at that value or that range. It is around, let's suppose it is somewhere at value of 1 or value of 1.5, 1.6 something. So the pH range, the pH curve is starting from value near 0, 1, 2, and then as we keep adding the base from the burette into the flask, then this curve start moving upward. Why is it moving upward? Because the pH value is increasing along the y-axis, so the values start increasing. But there is a kind of steady growth at this point. It is increasing, but not at a rapid pace. Instead, it is a slowly and gradually or steadily moving upward. But at one particular point that is mentioned or labeled as B, at this point, there is a drastic increase. There is a drastic increase or there is a abrupt increase in the pH value, and this is the portion which indicates as a reaction between an acid and a base on the basis of the equivalent amount of hydrogen ions and the hydroxide ion. I will elaborate this later. After this abrupt change or increase of the pH is completed, we then again have an gradual increase of the pH value from this portion. And when it reaches at point C, then the pH curve starts flattening. It is start flattening, and we have some specific value associated with this range. If we plot it along the y-axis, then it stops somewhere at the value near 14. Why near 14? Because again, the combination is of the strong base. And the strong base is basically somewhere around, the values of the strong base is somewhere around 12, 13, 14 pH value. These are the values of the pH. So that's why this pH is ending somewhere around this point. Now we have to uh, see what is happening. We have to see what is happening during this course of the this neutralization reaction. Basically, at the start, there was simply the strong acid present in the flask. But as soon as we started adding the strong base into the flask, the pH started increasing. But at this vertical portion, the amount of the hydrogen ions and the hydroxide ion became equal. The concentration of the hydrogen ions were become equal to the amount of the hydroxide ion. So at that point, there was a drastic increase in the pH value. So this is the range vertical portion. We have to calculate the midpoint of this vertical portion. For that purpose, we have to extrapolate the curved parts of the bottom and the top. These are basically extrapolated downward and upward. And the same way, these horizontal lines on at the start and at the end, they are also extrapolated. As a result of this extrapolation means to extend the lines to meet some particular point. We are extrapolating both vertical lines and the horizontal lines so that we can have some point at which they are meeting with each other. So they are meeting at these particular points. Now we take the half value or the half value or the midway value of this vertical section. That point is called the equivalence point. So basically, we are actually calculating the exact equivalence point of the uh, vertical portion. At this vertical at this equivalence point, the hydrogen ion is basically equal to the hydroxide ion. Now this means that after the equivalence point has been achieved, it will now start increasing its pH value, but it will then start it will increase slowly and steadily. And when this is in fact exceeded, the value becomes horizontal. Why is it horizontal? Because the extra amount of the base is simply increasing the pH value. It is not showing any type of the further neutralization reaction. The neutralization was already completed at this point. It was completed at this point. So after this, the value is increasing, but or in other words, only the well after this point, only the volume of the base is being added, or the volume of the base is being increasing, not the pH value, because after this point, only the particular value of the base, strong base, will be shown here. So it can have any value. Let's suppose 13.8. It can have 13.7, 13.6. So this value indicates that the strong base has now completely completed the or filled the flask in majority of the portion. So this was the titration curve for this combination, and all the information included in this passage is already explained. Then we have the second combination in which weak acid is reacted with a strong base. We will again do the same way, like we will initially have only the acid present in the flask, and then we will add the base from the bearer into the flask. So if it is the start, if the reaction is being started from the weak acid, which means that the pH titration curve or pH curve will start a value somewhere around 5, 6, 4, 5, 6. pH value is around 4, 5, 6, but less than 7, because this is the range at which weak acid is present. So the titration curve is increasing somewhere around this value, and we are adding more and more base into the flask. So it is increasing slowly and steadily, but again at this particular point, we can again see a sharp or drastic increase in the pH value. And after this drastic increase, there is again a slow or gradual increase in the pH value, but then it becomes flattened at this point. It is flattened at this point. And again, this flattening represents that the strong base pH has been established or achieved. Now, again, what is happening here? The weak acid is representing the pH of 456, but at this vertical portion, the amount of the hydrogen ions and hydroxide ions are now equal. One thing to note from the previous combination, that the equivalence point for the strong acid with the strong base is exactly at pH 7. So you have to keep in your mind that the pH value of the equivalence point for strong acid and base is the 7. However, this 7 is not attained in the other combinations if we have different types. For example, in this case, in which we are using weak acid with a strong base, then the pH 7, the pH of the equivalence point will be calculated in the same way as we did in the previous case. For this purpose, we should have the vertical section. This vertical section will be extrapolated upward and downward, as well as these horizontal lines are also extrapolated in their own directions. Now, these are the points at which they are meeting. These horizontal and vertical lines are meeting at these points. We have to take a half value of this vertical section. The half value of this vertical section is coming right at this point. This is a half value. Now we have to plot this value along the y-axis. Now along the y-axis, we can see that the value is around 9, which means the value is above 7. So the equivalence point of this combination is not 7, instead it is more than 7. So we do not refer to be equivalence point at exactly 7, which is the neutralization point for the uh, strong acid and base. However, it can also vary accordingly. Now we have already discussed about the whole story. And what about the last portion of the titration? The last portion of the titration is indicating that the strong base is now fulfilling the whole flask, or it is only the amount which is now in excess in the flask. That's why the pH is now attaining the value of the strong acid, just like the previous case. In the previous case, we also had the same ending point of the pH titration curve at this value of the strong base. So the later portion is the same. However, the initial portion is different because we started the titration curve from the weak acid, not from the strong acid. So all the information of this whole story is given in this passage, which you can read later on. Then the third combination. The third combination is of the strong acid with a weak base. Now we are starting with a strong acid, which means this portion of the titration curve, like the lower portion, is exactly the same as we studied in the strong acid and strong base combination. So this is the same type of the portion. We are starting the pH titration curve from the strong acid. But after that, we have now the equivalence point, or you can say this is the equivalence region, and from this equivalence region we have to determine the equivalence point. Now this after this, the weak acid will only be excess amount in the flask, but you can see here that this horizontal line, you can ignore this vertical portion. This horizontal line is now somewhere above the 7. pH 7 is below. However, the ending point of this weak base is above 7, which indicates that the weak base definitely has a pH value around, it can be more than 7, for example, 8, 9, and 10. So pH value is ending at somewhere around these values. That's why we have the ending portion at 8. Now, if we compute the equivalence point from this equivalence region, the value is below 7. Why is it below 7? We can clearly see here that the strong acid indicates values around 0, 1, 2 somewhere, and the ending portion is also somewhere closer to the 7, which means both the upper and the lower portion are now somehow decreased. When they are decreased, then we have the pH value below 7. And the same story goes for the previous case in which the acid was of the weak type, which means it was closer to the 7 from the lower portion, it was closer to the 7, but from the strong base, it is somewhere close to the 14, which means the whole portion has been now increased. That's why the pH value was more than 7 at the equivalence point. However, in this case, the pH value is lower than the 7. And then we have the last portion. The last portion of the weak base with a weak acid. Now, in this case, the weak base and the weak acid does not show a good type of the vertical portion. There is a difference here. In this case, the reaction is being started from the base, and then the acid is being added into the solution, into the flask. The reaction is started from the base, but acid is added. Because the same literature was taken from the endorsed Cambridge book, on which this particular graph was more clear as compared to the other resource in which I saw the type of the graph was like this. There was no clear indication of the equivalence region of the vertical side of the vertical region. So here you can see the equivalence point is not very clear. There is no distinct equivalence point, but the value is somewhere at pH 7. So pH 7 is the equivalence point of this type of the combination in which weak acid is added with the weak base. So here we have the equivalence point for this type of the reaction. There is no particular indicator which can be used for this type of the reaction or this type of the neutralization, which we will discuss later after the completion of this topic, how different indicators are used for the different neutralization type of the reactions. So we have discussed the type of the titration curve for the weak acid and base as well. Now these are the curves. These are the curves for the first three combinations. But here we started the here we are starting the reaction with the with the base, and then acid is being added, which means you are reversing the initial step. Previously we only had the base at the start, but acid in the start, but now we have the base at the start. So it is the same type of the reaction, it is the same type of the curve, only that it is now reversed. Previously it was this type, but now it is of this black type. So you can again have the same type of the vertical portion of the equivalence region for this combination, for this combination, and for this combination. We'll continue our lecture from this topic onward in our next class. Till then, take care and Allah Hafiz, everyone.